Oh,
Yes,
okay.
sir.
Then the person should link up with me. But then the requirement for this course is that you should have gone through and passed the Term 108 Introduction to Organic Chemistry. And now that you have not passed, it means that you are not even qualified to do this one. Well, but then I know they will give you an opportunity to write a receipt or a retake, and that one I know you pass. Link up with me if you have any challenge. But so that was just introduction.
Hello.
Yes. So
Yeah, hello, Doc.
yes, wisdom.
Yeah, please, the practical we did, no, for the first organic chemistry, no, they've not released the result yet, too.
Don't worry, you are 4 pass. They will release it. Okay.
Okay.
As for practicals, if only you turn out for the experiment and you did your report, I know they will publish it anytime soon. So let's keep our fingers crossed.
Okay.
But you'll be doing another practical alongside this course. This general organic chemistry also has a practical, and also go to the lab and do your practicals. But I was saying that the foundation we built with the introduction to organic chemistry is what we are going to build on for the general organic chemistry. Just that if you remember, during the introduction to organic chemistry, after I had introduced you to organic chemistry, organic compounds, and how they exist as mixtures, and how we can purify them, and how we can check whether they are pure, then going ahead to do elemental analysis, where you do the qualitative and quantitative analysis so that you can get to know the empirical formula. And when you know the mass, you can go ahead and calculate for the molecular formula. And when you perform other spectroscopic analysis like mass spec, IR, NMR, X-ray, then you can know the structural formula. And based on that, we said there are millions of organic compounds. And so we define functional group as the basis of which these organic compounds are grouped. So when you say functional group, it's just an atom or a group of atoms that give characteristic properties to a group of organic compounds so that they behave in a way different from other organic compounds. And based on that, we mentioned a number of these functional groups. One of them was the hydrocarbons. The other was the alcohols. We mentioned the carbonyls, that's the aldehydes and ketones. We mentioned the amines. We mentioned the carboxylic acids, and then the derivatives, that's the amides, acid chlorides, esters, and a number of them. But if you recollect, we said that the introduction to organic chemistry was supposed to be limited to only the hydrocarbons. So that was what we did in the semester 1, block 1, where our attention was only focused on one functional group, the hydrocarbons, where we dealt with the alkanes, alkynes, and I don't recollect whether we were able to, I'm sure we were able to get to the aromatics, the benzene. So now, the general chemistry is going to look at other functional groups. Oh, my slides are not showing.
Yes, no, please.
Yes.
Oh, so you can't see the alcohol?
No,
No,
please, we can't see anything. Only your picture.
Hey. Oh, no. But then I'm sure you have the slides because I gave the slides out to to one of your colleagues. What's the name? I think she's a course rep for the UCC Center.
Please, she has already shared it on the platform.
Yes,
that's Kafui.
Yes, so Kafui has shared the slides. There are a number of them, but I just decided not to frighten you with the plenty slides that we are going to deal with. So I only released that of alcohols, ethers, epoxides, and then the carbonyls. But then this course generally is going to deal with a number of the functional groups, i.e., we're going to look at alcohols, we're going to look at ethers, we're going to look at epoxides, we're going to look at the aldehydes, the ketones, then we move to the carboxylic acids. Now, when we get to the carboxylic acids, it has a number of derivatives, but we'll be looking at 4 of them. We'll be looking at the amides, which are derivatives of carboxylic acids. We'll be looking at the esters, which are derivatives of what? Carboxylic acids. We'll be looking at the anhydrides, and then we'll be looking at the acid chlorides. Now, when we are done with all the derivatives of what? Acid, we will then move to another functional group, that is the amines. And from the amines, we will proceed straight to introduction to stereochemistry, which the chemistry people have done it last block, the block 1. They did it as a whole course, stereochemistry. But in your case, I am supposed to introduce you to stereochemistry. And so that will be the advantage the chemistry major people will have. Or they have dealt with stereochemistry, and their papers are in front of me as I am yet to mark. But if time will not allow us, okay, that is the course outline, as I've indicated. Wherever we will get to, of course, that is where you'll be examined up to. Okay, so it means, please, you can still not see my slide, eh?
Still, you can see.
Yes,
okay, let me stop and then present again. I don't know what's happening, but let me see. Please, is it showing now?
Yeah.
Yes,
All right. So you have the slides, and it's supposed to be a guide. And with time, I'll be sharing some tutorial questions and then some review questions with her to share with the class as well. So like I was saying, we will see where we will get to, because apparently we have just 4 weekends to touch on all this. So it depends on how we move, the rate and the pace at which we move. I will advise that if you don't understand anything, please don't let me move fast. Let me explain so that you get an understanding in the basics. Because when you find yourself teaching chemistry, your student will be asking you questions, and you should be able to address their concerns. But then again, some of the questions too, I would advise that you keep it to yourself so that I can move fast, so that we can cover as many items of my table. So we're starting with alcohols, and this is a common organic class of compounds. And I'm sure you might have all heard of alcohol. I will want one of you to tell us what alcohols are. They are also called alkanols. What are they? anything at all that you know. Yes.
Okay, so can we say that they are hydroxy compounds characterized by the presence of the hydroxyl functional group?
You said they are hydroxy compounds.
Compound characterized by the presence of hydroxyl functional group.
So what is the hydroxy functional group? You say that's their characteristic. What is the hydroxy functional group? What group is that?
That's the OH.
That's the OH.
Yeah.
Okay. Now, so let me ask you, you know water?
Yes, please.
Water is H2O. That is hydrogen bonding and OH. So there's a hydroxyl group in water.
Yes, please.
Isn't it? All right.
Yeah.
Can we say that water is an alcohol? Can we then say that water is an alcohol? Because this functional group called alcohol that we are talking about, if it is found in any organic compound, it gives a particular characteristic behavior and properties. So if you say hydroxyl functional group,
it should rather be attached to the alkyl group.
Oh, okay. So the hydroxyl group should be attached to an alkyl group.
Alkyl group, yes.
Okay. Can we get another person who also wants to say something about alcohol?
Yes,
okay,
sir.
Doc. An alcohol is an organic compound that has a hydroxy group attached to a saturated carbon.
Okay. So Aaron too is saying that an alcohol is an organic group or an organic compound that has the hydroxyl group attached to a saturated carbon. Now, look at his choice of words. Now, in the introduction to organic chemistry, we all got to know the saturated alkanes and then the unsaturated ones. That's the alkenes and alkynes, right? So when he says a saturated carbon, definitely we are referring to an sp3 hybridized carbon. We are referring to what? An sp3 hybridized carbon. That is the carbon atom in alkanes, where we have carbon single bond carbons. All right. So if you have an OH or the hydroxyl group bonded to hydrogen in the case of water, then that can never be an alcohol. In fact, water itself is not even organic. Is water organic? It is not, because organic compounds are carbon containing compounds, and water is not organic in the first place. And then again, the hydroxyl group there is not bonded to an sp3 hybridized carbon or a saturated carbon. So water cannot be said to be an alcohol. So my next question is, can we give some examples of alcohols that we know? Alcohols that we know. Any known example? This one, yes, I want those who have never spoken in my class to talk. There are some people, they will never talk. I don't know whether when they speak on online lectures, whether they will tend to ghost or whatever it is. They will never talk. Please, this is an opportunity for you to talk. Yes, one of them is, the hand is up, Atapol. An example of an alcohol. Yes, Yabua.
An example can be the methanol.
Methanol. Yes, methanol.
Or
methanol. Methanol. But Yabua, have you seen methanol before?
Honestly, no.
So something that you have not seen, and then that's what you are mentioning as an example. When I ask you for examples of things, talk about things that you have seen, that you have touched, that you know. Yes, Priscilla.
Ethanol.
Ethanol. Ethanol. Priscilla, have you seen ethanol before?
Yes, sir.
Okay. The last one, forgive. An example
Yeah,
of
sir.
an alcohol.
Sanitizer.
Sanitizer. Is sanitizer an alcohol? You have mentioned it, you say sanitizer. Is it an alcohol or it contains alcohol?
It contains alcohol.
All right. All right. So now we can mention some examples. Then let's look at the importance of alcohol. If in an exams I ask you, give me 2, 3, or 4 importance of alcohol. What are they? Importance of alcohol. Yes.
They can be used as cleansing agents.
They can be used as cleansing
agents.
To cleanse what?
Okay, so stained blood.
Stained blood.
Yes, please.
Why would you want to use alcohol to clean stained blood?
Because it dissolves, stained blood or blood dissolves easily in alcohol.
Why not use water? Because you could easily use water.
Water may not be able to clean the blood totally, but
water
partially.
is a universal solvent.
Yes, but then it dissolves almost means not all, almost all the solutes.
Okay, so what is it about blood that will make alcohol to be able to dissolve or clean, but water cannot? Anyway, that's just another day's. Well, so yes, that is what he has to say. Any other? I see some hands up. Emmanuel.
Okay. Hello, sir. Please, that it is used in the food industry.
Yes, in the food industry, alcohol serves as a beverage, isn't it?
Yes, please.
In the food industry, alcohol serves as a beverage, and there are a number of this alcoholic beverage. Okay, you can talk about kasapa. Is it kasapa? Kasaprekun. Yes, kasaprekun. You can talk about alomo bitters. You can talk about Guinness. You can talk about what? What?
Opening bitters.
Opening bitters. Alomo bitters. What again?
Adonko bitters.
Adonko, Fameko. All right.
So you guys will be drinking, eh?
Now, the kind of example that is coming, let me hold on and ask you a new question. Have you ever taken alcohol before?
Yes.
No fish eyes. Say the truth.
Yes, sir.
If you are taking alcohol, if you are taking alcohol before, I want to see by hand. Okay. Okay.
For everyone.
Everybody has taken alcohol before.
Everybody. Not
yes.
Okay.
Because you can find it in food.
All right. So then let me put the question this way. Is there anyone here who has never taken alcohol before?
Not really.
Is there anyone here?
Yes.
All right. So it means we have all taken. Me, I have not taken alcohol before.
It's never true.
How?
Yes. Because because my doctor tells me that I have not the very day I will take alcohol, I will die.
Hey.
Yes.
It's not true.
No.
Maybe not direct
You have
you,
to start.
not direct, but indirectly you have taken it.
All right.
So you can find it on food.
Okay. So patience, you are right. So all that we are saying is that you know, if you look at the food we eat, okay?
Yeah.
If you look at the food we eat, over 70% of the food we eat on daily basis contains alcohol. Okay. Yeah. Yes. And you know, we eat a lot of carbohydrate food, and carbohydrates can be, you know, that is can be oxidized to what? Alcohol. Okay. And even if you have also paid attention to most of the medications, the drugs, okay, if you go to a pharmacy shop or a drugstore to buy a medicine, you can also see that most of the medications have alcohol as a composition, okay, either the solid or the liquid drugs. Some of them, they even use alcohol as a storage medium for most of the drugs. And so a lot of the medications that we take contains what? Alcohol. Again, even the human body itself, as you are there right now, the human body itself produces its own alcohol because a number of the activities or processes that takes place in the human body, like digestion and all those things, sometimes requires alcoholic medium, you know, for those processes. Remember that it is alcohol is one beverage that when you are happy you can take, isn't it? When people are happy, they take alcohol. And when people are sad too, they take alcohol. Okay, so in the times where you are jubilating, you are happy, you take alcohol to have fun, merrymaking. And then when you are sad too, let's say you are bereaved, sometimes you say, let me go and take alcohol just to manage the sadness. So some people, when there is somebody die in their family, it is an occasion for them to taste an alcohol. You know, they use that as a case to go and then take some alcohol.
Sometimes when you want to speak your mind, you have to take alcohol so that you can, you know.
Sometimes when you want to speak your mind to especially to a superior,
talk to your in-laws.
Yes, just so that you can. It's like you are not seeing well, but you'll be saying things. All right, but you know that people also even go and take some alcohol before they go in for their food diet. They call it yebudidi, just to give them some appetite.
It's very necessary.
So there are so many ways in terms of as a food or as a beverage, alcohol can be used. So yes, aside that, what other? Alcohol is used as a fuel.
For making medicine.
Alcohol is used as a fuel. Alcohol serves as what? Antiseptic, okay? It serves as what? Antiseptic. In fact, if you go to the hospital, before maybe the nurse will give you an injection, you see that they will rub the place where they are going to give you the injection with what? Alcohol.
I think that's sterilizing.
Yeah, just to sterilize and clean if there are any germs or whatever there. And even if you go to the lab that you are going to take a blood sample, before they even use the syringe to take your blood, they will rub the place, your skin, just to sterilize and then clean any microbes that might be there. The guys, if you go to the barbering salon after shave, you see that they will rub the edges of your head with what? Rubbing alcohol. Rubbing alcohol is as a proper alcohol. So yes, as a disinfectant, it is used in that way. So there are a number of importance that we get from alcohol, and you have listed some, and you are right. So on the screen, you can see R bonded OH, that is the alcohol functional group. And then here we have the epoxide functional group. And then we have the ether functional group. So we are going to now pick the alcohols. And please, for each of the functional group, general formula, we look at their structure, we look at their physical properties, we look at their nomenclature, how to give them a name, IUPAC name. We look at their synthesis or preparation, we look at their reactions. So that is that. And in some cases, we will also look at classifications that are found in them, as well as sometimes isomerism. So let's continue from there and look at the alcohol. Their general formula. Please, I hope you can see the screen.
Yes, Doc.
Yes, their general formula is CnH2n plus 1 OH. Okay, and the N is an integer from 1 going. Or you can also say their general formula is what? R bonding OH. And like we said earlier on, the hydroxyl functional group, which is a functional group of alcohol, should be bonded to a saturated carbon or an sp3 hybridized carbon. So take note of that. This is methanol alcohol. And so we want to use that one for you to know the bond angle. That's the alcohol functional group. The bond angle, meaning the bond between the carbon oxygen OH is not linear. It is not linear. Okay, it is bent. And then the angle is what? 108.9 degrees. 1.8.9 degrees. Now, on the far right here, you see a compound here where there's a hydroxyl group OH bonded to an aromatic nucleus. But we say that it's not an alcohol, but it's what? A phenol. Remember that in benzene or the aromatic nucleus, the carbon atoms there are in what? sp2 hybridized state. So if you have an OH or a hydroxyl group bonded to them, that carbon is not saturated. That carbon is not an sp3 hybridized carbon. And so you cannot refer to that one as an alcohol. Such compounds are called phenols. They are called phenols. So know the difference between an alcohol and then a phenol. And then again, know the difference between an enol, a phenol, and then an alcohol. An enol, a phenol, and then an alcohol. Know the features, the difference between them structurally. Yeah, so with examples of alcohol, we have methanol, ethanol, 2-propanol, 2-methyl-propanol, pentanol, hexanol, and so on and so forth, a number of them. And then we have also given examples of some alcoholic beverages. And that one, I could see that the examples were coming plenty because we could relate very well. Now the structure and shape of alcohols. So we know that the functional group is the OH group, which should be bonded to an sp3 hybridized carbon. The bond angle of the hydroxyl group is approximately 108.9. And then the oxygen atom, that's the oxygen in the hydroxyl group, is what? sp3 hybridized. If you take the alcoholic or the alcohol functional group, we have the alkyl group, That's the R, and then we have the hydroxyl group, and together that constitutes the alcohol functional group. That constitutes the alcohol functional group. So that is how the structure of alcohols look like. Now let's go ahead and then get to know how to name them. How do we name alcohols? I presume that the IUPAC rules we learned. Is there a hand up? Yes, wisdom.
Yes, I wasn't seeing the screen, but now it has come.
Please, can you go back to the structures and the shapes of alcohol?
Oh,
I should go back to
the structures and the shape of alcohol.
All right. Here.
Yes, please. I didn't get that. So please, can you reframe that for me?
Oh, so I was just saying that if you pick any alcohol, okay, this is how the structures look like. You have the alkyl group, okay, the alkyl group, which can be 1 carbon, 2 carbon, 3 carbon, chain. But what is important is that the hydroxyl group, okay, is always bonded to what? A saturated carbon. That is an sp3 hybridized carbon. Then again, we are saying that this hydroxyl functional group, the OH, okay, it is not linear. It is not bonded to the alkyl group in the linear form, but rather it is bent, okay? Like here, it is bent, and it has this bond angle of 108.9 degrees. And then the oxygen atom in the hydroxyl group, we are saying it is in an sp3 hybridized state. So this is what I said about that. And so we are moving to the nomenclature of alcohols, how to name alcohols. So apparently I was just making a reference to the point that we still remember the IUPAC names that we were exposed to in the introduction to organic chemistry. When we were naming alkanes, we said you select the longest continuous carbon chain, and then you give the corresponding alkane name. Any other group that is outside that chain is considered what? A substituent. And then you number the substituents such that you give them the least position. So whether you number from left to right or right to left, have in mind the position of the substituent, and it should always be the least. Then we said that when you have 2 kinds of a particular substituent, let's say methyl group and another methyl group, then you introduce the prefix di to denote the 2. So you have dimethyl, but then you indicate each one of them's position. If they are all on the same carbon, let's say carbon 2, it becomes 2,2 dimethyl. If one is on carbon 2, one is on carbon 3, it becomes 2,3 dimethyl. The same thing applies to other substituents if you have 2 or more. If you have 3, you say tri. If you have 4, tetra. And I'm sure you remember that. Then again, we said, as much as we are doing organic compounds, we could also have inorganic substituents, like the halogens, chloro, fluoro, bromo, and the rest. So in a situation where you also have multiples of that, I'm sorry, if you have any of them appearing twice, you can also introduce the prefix di. If it is 2 chlorine, dichloro. If it is 2 bromine, dibromo. Then when you have 2 or more different of an inorganic substituent, IUPAC says that we should arrange them in what? Alphabetical order. So let's say you have a bromo substituent, you have a chloro substituent, and then you have an ido substituent. In alphabetical order, B, bromo comes first, followed by C, chloro, and then I, ido. So when you are writing them as substituent names, you arrange them in alphabetical order. The same thing applies to the organic substituent. If you have, let's say, a metal substituent, an ether substituent, a proper substituent, then alphabetically, E, that's ether, comes before what? M, meter. And then M, meter, also comes before what? P, proper. So in that way, you arrange them in order of what? In alphabetical what? Order. But then the last point here is that if you have organic, then inorganic substituent, or in a compound, then always make sure you bring the inorganic substituent first before you proceed to the organic substituent. Please, I hope you remember all these rules. I'm just trying to recount and recollect so that if you have forgotten, you can refresh your mind. So I'm sure we do remember them all. Now, we are here to name alcohols. So if you are naming an alcohol, then this time around, when selecting the longest continuous carbon chain, that chain should have the alcohol functional group to be picked. That chain should have the OH, the hydroxyl group, to be part of that long chain, and that becomes your parent name. Then after selecting the longest chain that contains the alcohol functional group, if there is any other group that does not form part of the chain, we consider that as what? A substituent. And the rules of naming substituents, I have just recapped them, so you know what to do. Again, when we say an alcohol, it does not mean that the functional group OH can or should always be one. Sometimes you can have two of the alcohol group or three. That is where we are heading towards the polyhydroxy alcohols. You know, the diols are two OHs, but when you have 3, 4, 5, 6, 7, 8 going, then we talk about the polyhydroxy alcohols. In the case where there are two of the alcohol functional group, you introduce the prefix diol. If there are 3, triol. If there are 4, tetraol. If there are 5, pentaol. So depending on the number of the hydroxyl group, you can introduce the prefix di, tri, tetra, penta, and so on and so forth. Now, if you want to name an alcohol and you say select the longest continuous carbon chain, and you do, and then let's say the chain is 8 carbon, you will need to consider the corresponding alkane name. And a corresponding alkane name for 8 carbon will be what? Octane. And so to get the alcohol name, you omit the last letter E and then replace it with what? OL. So the octane becomes octanol. If the carbon chain is 7, then the corresponding alkane name, which is what? Heptane, becomes heptanol. 6, hexanol. 5, pentanol. And so on and so forth. So then again, I'm sure you've not forgotten the hydrocarbons names. Now, because the functional group is the alcohol, the OH, when we were naming alkenes, we said after selecting the longest continuous carbon chain containing a double bond, number the longest chain so that you give the least number to the double bond. When we go to alkynes, you number the longest chain so that you give the least number to the triple bond. So the same thing applies to alcohols. After you know your longest chain, now number that chain so that you know the position of the alcohol functional group, whether it's on carbon 1, carbon 2, carbon 4, carbon 8, or what have you. And that particular position should precede the parent name. Should precede the parent name. Okay, it should precede the parent name. So that if you have 8 carbon with the alcohol functional group on position 3, then okay, if the alcohol is on the carbon 3 on an 8 carbon chain, then it becomes 3-octanol or octan 3-ol. Any question up to this point on the nomenclature of alcohols?
Please, is your slide moving or still on slide 7?
Still on the same slide. I've just paused to find out. Yes, Wisdom, your hand is up. Wisdom. And then Emmanuel, your hand is up. Any question?
No, please.
If there are no questions from you, then you can lower your hands. So, aside this information that I've given you about naming of alcohols, all the previous rules that we know also applies. Now, we also have the common names, but then that's not our focus. Our main focus is on the IUPAC names because that is what is internationally accepted. But then we also have the common names. Sometimes you need to know some of the common names. All right, so now on the screen are examples of alcohols and their names. Now, for each one that the names are 2, we have the IUPAC name and then the common name is in the brackets. Okay, the IUPAC name and then the common name in the bracket. Based on the rules I've given you, kindly look at the examples on the screen and see whether you do appreciate the names, whether you agree that these are correct names, and if you have any question, you let me know. So I'm giving you some time, 1 or 2 minutes, to look at them, each one, and you yourself, try your hands on and see whether you get the same name as captured on the screen.
Sir,
Yes.
please, naming of the first three, for that one I understood, but the second ones, I don't understand why it is 2 butanol and 2-methyl 1-propanol and the other one. So I don't understand why their naming is like that.
Please hold on and give me a second. I'm going to respond to it.
Okay.
Okay, so your question again. Your question again.
I'm saying that like the first one, I understand that the carbon chain is 3 carbon chain.
Yes.
And we have 1 propanol.
Yes.
And the other one is a double bond and 3 carbon chain.
Where?
And
where is the double bond? There's no double bond here. This one.
That one is it not a double bond?
No, there's no double bond here. Can you see an alkene here?
Okay.
It is just it's just 1, 2, 3 carbons. The same as this one. 1, 2, 3. Okay. Just that for the first one, the functional group OH is bonded on the terminal carbon here. So you can see carbon 1. Okay. But over here, the OH functional group is bonded to 1, 2, the second carbon, if you are to number the longest chain.
So why 2 propanol?
Why 2 propanol? Because the OH, the functional group, the position is 2. So if you have 1, 2, 3 carbons, number that chain, okay? And you realize that the OH is sitting on the second carbon. That is the position. So 2 propanol. The over here, if you number from here, 1, 2, 3, the OH is on the first carbon. That's why it is 1 propanol.
Okay.
Hello, sir.
Yes.
This thing, please.
Is it Festus?
Yes, sir, it's Festus. So your Festus, the first one, sir.
So far as you were able to survive the introduction to organic chemistry, I know you will survive this time around too.
I survived.
Yes.
Sir, please, just a recap here. Looking at the first one, supposing there's no OH, there's no OH, the carbon, the number of carbons would have been 4, right? 1, 2, 3. Or that
it will not be 4. It will not be 4 because now this is what we call the bond line method. Okay. So beginning of a line is a carbon.
Okay.
Is that right? The end of that line is a carbon. So there's a carbon here. Now between the 2 carbon is a bond. It's a bond that is joining them. Okay. Now, if you also take from here, there's a bond that is linking this carbon and then the carbon here.
All right.
The third carbon. Now, this third carbon and then the oxygen, that is the bond you can see there. So between the oxygen and then the carbon here, that is the bond. So if the OH is not there, that bond will not be there. And then the carbons will be left with 3, and that will be propane. So here, if you are unable to get your carbons counted well, then you are going to be in hot waters. All your names will be wrong. All your names will be wrong if you don't get the carbons well counted. Over here, you
Sir,
have
please, sir. Please, can you draw out your lecturing so that we can also understand it well?
Yes, I'm going to do that. In fact, I was doing that when I gave you the 2 minutes to look at this one. So what I'm going to do is I'm going to project my chem draw Okay.
Exactly, so that you can draw them.
So
and
that
pull
I
off
have
the
already
draw.
drawn some of them there, but I'll just try and then draw another one and then we move on. Okay.
Thank you.
But sir, my problem is the 3 and 4. The 3 and 4, since we are having 5 carbons there, but it seems you are using the butane. I don't get it.
You mean is it this one or this?
The
is it this
third one, yeah.
This
the
one.
Naming.
Is it this one?
I can't see your cursor.
Oh, you can't see the cursor. Wait,
Yeah,
hold
yeah.
on.
Okay,
Hold on,
yeah,
hold on,
I can
hold
see
on.
it now. I can see it now, sir.
You can see my cursor now.
Yes.
Are you referring to this one?
Yes, that one is for the 4th one, and the 3rd one at the top here. It seems the carbons are 5.
No,
they are not 4.
4. It's the same thing that Festus was drawing attention to. It is 1 here, 2 here, 3 here, 4 here.
Then 5.
Where the oxygen is bonded, it's just a bond. It's oxygen that is there. So we're just showing a bond between this carbon here, the 4th one, and then the oxygen. There's a bond that's linking them. So you don't consider that one as a carbon. If you consider that one as a carbon, then you have to draw another bond down.
Okay, so international is uncle OH be any what dear uncle, be fan a carbon is all.
Exactly.
So we shall cry who say and on a line a shorter than the carbons need a hydrogens needed. That's another observation, Myers, because we first one and last one who say no bond in one any a shorter.
Yes. So all the
I can
all
see
the carbon OH bonds look a bit
as
short.
compared to the first one. Okay. Yeah, I get it.
All right.
Thank you.
But then, so like a colleague of yours said, you will now appreciate that all the names here are correct. 1 propanol, 2 propanol, 1 butanol, 2 butanol, 2 methyl, 1 propanol, 2 methyl, 2 propanol. You agree? So now let's pick some more examples and illustrations.
Please, I have a problem with the 6th one. I am looking at the 6th one.
I have a problem with this one.
I think the methyl group are 2.
Here, you say you have a problem with this one?
The 6th one.
The 6th one. Can you see my cursor?
No, it's not showing.
Sir. It's not showing. Yes, sir. Yes, sir. That one.
Yes. Is it showing?
Yes, sir. This one, that one.
Yeah. What is your problem here?
I think the methyl group is supposed to be 2 there.
Yeah, but we have 2 though. 2 methyl.
No, the 2 methyl is telling the position of
the carbon, the number of carbon.
Okay, so now let's you see, we just have to apply the rules. So you see, the same knowledge we had in the naming of alkanes, that's what we are bringing here. Just that here we are talking about alcohol. So we are saying that select the longest continuous carbon chain. Now, if you select 1, 2, okay. If you select 1, 2, and you end here, that is not the end of that chain. It can either go up or come down. So it becomes 1, 2, 3. It's still continuous. Or you can start from the top here. 1, you come to this 1, 2, and you come down here 3.
Yeah, so it's only 1 meter.
And then end here. Is that right? Make sure that the carbon skeleton that you are selecting is continuous. So from one end to another end. It does not stop in the middle of the chain. Please, are you okay now?
Yes, sir. Yes, sir. Yes, sir.
Good. So now let's
Hello, sir.
Yes.
Sir, please, the first one, TETs. I'm confused about that one. The TETs in the brackets. TETs,
okay, so
alcohol.
All right, so the TET butyl alcohol. I remember when I don't know whether if I had the opportunity to teach you then, but then we were saying that apart from the IPAC name, we also have the common names or the semi-systematic names. So we have something like iso. When you see iso, it means 2 methyl groups at the end. Then we have the neo, where you have 3 methyl groups at the end of a long chain. And we also talk about sec and then tet. Okay. Now, in the case of the sec and then the tet, now if you didn't have a problem with this one, you see that the 2 butanol, we say it's what? Sec butyl alcohol. What it means is that the OH is bonded to what? A secondary carbon. And remember, in the introduction to organic chemistry, I classify carbons as what? Primary carbons, secondary carbons, tertiary carbons, quaternary carbons. And we said that a primary carbon is bonded to only one other carbon. A secondary carbon is bonded to 2 other carbons. A tertiary carbon is bonded to what? 3 other carbons. And a quaternary carbon is bonded to what? 4 other carbons. So now, in the common name, if you take the 2-butanol, the common name, okay? Now, what you can see is that, let me use my cursor. What you can see is that where the alcohol functional group is bonded, that carbon is a secondary carbon, because this carbon here is bonded to this carbon 1 and is bonded to this carbon 2. So it's a secondary carbon. So you say what? Sec. Secondary, from the word second. Secondary, sec. But then the total number of carbon is what? 4. 1, 2, 3, 4. But then the alcohol is bonded to a secondary carbon. That's why we said what? Sec-butyl alcohol. So over here to the text, the alcohol group here is bonded to this carbon. Now look at this carbon. Is it a tertiary carbon? If it is, then it becomes tet-butyl. And this carbon here is tertiary because it's bonded to 1, 2, 3 carbons. So it's a tertiary carbon. And then if it's a tertiary carbon, that's why we call it tet. And it's butyl because it has 4 carbons involved. Okay. So that is that.
Thank you very much.
Good.
Thank you.
With all these questions that you are asking, it means you people, you blow my exam. So
yes.
All right. So now I will continue sharing this again, but then let me project my chem draw so that we can have our hands on more examples. Please, can we all see the screen?
Yes, please.
Yes, sir.
All right. So I have already, whilst you were trying your hands on the one I had showed you, I was behind the scene drawing this different alcohol because apparently I'm going to let you name them yourself. And then we check whether you are correct. But then, like somebody said, I want to draw one of them. Let me draw one of the alcohols. So I picked, can you see the whole, the 2 bar? I pick a bar, okay? That's a bond. Please, can you see it?
Yes, Doc.
Yes, please. Yes,
Good.
please.
Now, as you can see it, it's like one line. But then beginning of the line is a carbon. Is that right? Now, the end here is also what? Another carbon. So this is a 2 carbon kind of thing. So you can call it ethane. Now, if I want to extend the carbon chain, I will put the cursor here at the end here and click. Then another bond joins another carbon. So this is the 3rd carbon. So you have 1, 2, 3. Is that right? Please, can you see the 3 carbons? 1,
Yes, sir. Yes, sir. We have
2,
three.
3. Now,
Yes, sir.
without any alcohol functional group, there you can see this as 3 carbon because it's an alkane, propane. But if I introduce an OH at the end. Okay, so I want to type the OH. So I put the cursor here, and then I type in my OH. Okay, as soon as I type in my OH, what it means is that this carbon here is bonded to this carbon here, and the carbon here is now bonded to what? Oxygen. So you cannot say that it is still 3 carbons, because now this line here between the oxygen and this carbon is now a bond. It's representing a bond. So between the oxygen and then the carbon here, there's a bond. So it means that this is a carbon and this is oxygen, and they are being connected, they are being linked by a bond, a single bond. And this carbon here and this carbon here is also being linked by what? A single bond. I can introduce double bonds and triple bonds. So if I introduce a double bond, so it means that there is a carbon here, which is double bonded to this carbon, and it is single bonded to this what? Oxygen. And so forth. So that is how these bond line structures are drawn. Now, let me take away the alcohol. So now you see there. So now it's considered as alkane. So it's 3 carbon. 1, 2, 3. So if I want an alcohol of 3 carbons, I don't just attach the OH here. I have to show a bond again. Okay, I have to show a bond again where the 3rd carbon is, and then before I can attach my alcohol, so that I will have a 3 carbon what? Alcohol, which will be 1, 2, 3, and then this bond to the oxygen. So it's a 3 carbon alcohol. So please, I hope you are okay with the dot line method structures now.
Yes, please. Yes, please.
Good. So now let's go to our naming. Now I have drawn about 5, 6 alcohols on the screen. So I want you to pick any one of them and then give the IUPAC name. So you just put up your hand, I'll mention your name, and then you tell me the one that you want to. Yes, Harriet, your hand is up.
Yes, sir. Please, I will answer question 1.
Okay.
So it's 2-methyl 3-propanol. 2-methyl, yes, 2-propanol.
Come again.
2-methyl 3-propanol. 2-propanol, yes. The methyl is on the 2nd carbon, and then the alcohol too is on the 2nd carbon.
Okay. Will someone also want to say something different?
Sir, 2-butanol.
Yes, sir. What are you saying?
2-butanol.
2-methyl-propan-2-ol.
2-methyl-propan. Is it different from what Harry said?
No.
Yeah, so you decided to bring the position in the middle of the parent name. That is also correct. That's also correct.
Let me do number 2.
So I have used, you see how have you seen the name there?
Yes, sir.
So do you know how I got the name? So
No.
now I hope you are watching. Can you see?
Yeah.
Yes, sir.
So I select the whole molecule, and then I will right click it, and then you see that there. I hope you can see all these words here, all these items.
Yes, please.
And I'll scroll down, and then I'll get to a place called analysis. Okay. Now with the analysis, you can see the name, the chemical formula, the exact mass, the molecular weight, and then the elemental analysis. So any one of them that I want, I can pick. But if I select all, it will give me the name, it will give me the chemical formula, it will give me the exact mass and everything. So now let me select the name, and then it appears 2-meter propan 2-ol, or 2-meter 2-propanol.
So please, can you explain that for us?
Explain what?
How you got 2-meter propanol and 2-ol.
So now, the structure here, the longest chain, select the longest chain that contains the alcohol. So it can be 1, 2, 3. Okay, 1, 2, 3 is the longest chain. If that is the case, then it means that this carbon here, methyl, is a substituent. Is that right? Now the 3 carbon chain, number it so that you give a position to the alcohol. So if you number from here 1, 2, 3, then it means that the OH is on the second carbon. If you also number from right to left, 1, 2, 3, the OH is still on the second carbon. So the alcohol position is 2. And then the longest chain is 3. So we are saying that the longest chain is a 3 carbon. So what is the corresponding alkane name? It's propane. It's propane. Now, because it is not an alkane, but it's an alcohol, the last letter E, omit it and add what? OL. So it becomes propanol. Then, when you number the longest chain, the alcohol functional group is on the second carbon. So that is the position of the alcohol functional group. And that 2 can come before the propanol or in the middle of the propanol. So it's either 2-propanol or propan 2-ol. Then we know after the longest chain, any group that is outside the chain is a substituent. So now this methyl group here is a substituent. And you have to number or name the substituent before the parent name. Now the substituent group methyl is also on the second carbon. So you also have to indicate the position of the methyl, which is what? 2. And then you add the methyl and then the parent name. Does that make sense?
Yes, sir. Thank you.
Good.
Yes, sir.
So I want somebody to pick the second one, and then we
Okay,
check.
so let me take the second one.
Let me take the second one.
So
Patience. Yes, let's allow patients to do that.
yes, the second one we have 6 carbons, making it hexane or what? Yes. Then we have the alcohol on the first carbon. So I named it hexane 1-ol. Am I right?
Hexane 1-ol. Okay.
Yeah.
That's a good attempt.
I also did it 1 hexanol.
1 hexanol. Hexane 1-ol is the same thing.
Hexanol, yes.
Is there anyone who is
I just said
getting a different
hexanol.
name?
Am I correct?
Now,
I just said hexanol.
Nimatu, you said hexanol, right?
Yeah.
Yes.
Okay. Hexanol, you are not wrong, but sometimes it depends on the marking scheme. If I'm in a good mood, I will mark you and give you the mark. If I'm not in a good mood, I will subtract some marks. And the reason is this. Oh no, I can always be in a good mood. So the reason why the position is important is that if we remove this OH from the carbon 1 here, okay, we have 1, 2, 3, 4, 5, 6, isn't it?
Yes, sir.
Now, if we bring it here, sorry, let me go back. If we bring the alcohol here instead of this side, are you still going to call it hexanol like this? Are you going to call it hexanol? No.
No, please. No.
This time around, you call it 2-hexanol, isn't it? So whenever the longest chain, that 6-carbon chain, you have other positions that you can locate the alcohol and it will give you a different name. It's important to indicate the position. Is that right?
Yes, sir.
Let me give a last explanation. So if I have this, and then this, and then I bring my alcohol OH here. All right. Now this one is what? A 2-carbon alcohol. 1, 2. Is that right?
Yes,
So,
please.
if we say 1 ethanol, you are correct. Is that right?
Yes.
But the reason why it is not important for you to bring the 1 here is because this alcohol is on this carbon as 1. If you remove it from this carbon and you bring it here, that one becomes 1. And it is still what? 1 ethanol. So irrespective of which carbon the OH is put on a 2-carbon chain, you will always get 1 ethanol. It will not change the name. So we say ethanol. We just say ethanol. It is not important to bring the 1 because whichever other carbon that you put the OH, you will still get the same what? 1 ethanol. So there's no need of bringing the 1. But where the longest chain, you have other positions that you can locate the OH, and that will give you a new name like this one. Then we say, please indicate the position so that you get what? 1 hexanol or hexan 1 or. I want to go back to the old structure. So this was what was there. All right. So the names that we've gotten are 1 hexanol, hexan 1 or hexanol. So let me generate the name and then let's see whether it is closer to what we have given. Have you seen it? Have you seen the name?
Yes, we can
Yes,
see
Doc.
it.
Yes,
Doc. Hexan 1 or.
Yeah, I'm right.
So you see that they brought the 1 in.
Yeah.
The reason why they brought the 1 is that there are other carbons that when you put the OH, you won't get hexanol. You get either 2 or 3 hexanol. So it means that to differentiate, for us to know that it's a 6-carbon alcohol, but then the alcohol is on the first carbon, it is important to bring the 1. Can we go to the third one?
Yeah, let me name the third one.
Yes, sir.
Yes, go ahead.
The third one is 2,3-meter 1 heptanol.
Doc.
Doc, hello.
2,3 diameter, 1.
Relax. Hello, please relax. Relax.
Calm down.
I know all of you have tried your hands on it, isn't it?
Hello.
All of you
Can I come on?
Oh, relax. All of you might have tried your hands on it. So let's pick one at a time. When somebody says it, then we compare with ours and see whether we are on the same page or not. If we think we have a different answer, then we also say ours. So now let's take the first person.
Francis is here.
Kwabena?
Yes.
Is it Francis? France. Okay.
Sir, I will take it as
What are you getting?
2,3 diameter, 1 or
2,3 diameter heptan 1 or.
Yes.
Heptan 1.
Okay. Can we get a different one? Yes, Tayu.
Doc, I had 3 diameter, 1 heptanol.
2,3 diameter, 1 heptanol. 1 heptanol. Yes, can we take the third person? Anyone that is different from these two, because the two of them, what they are saying is the same. What Kwabena said is the same as what Tayu also said.
So it's 2, 3.
They don't have the same thing.
If yours is the same thing,
2, 3,
don't give it. I want somebody with a different name.
Okay.
So it means we all agree to what it's giving us, isn't it?
Yes, sir.
Okay, so let me check and let's see whether.
Heptan 1 or
2-3 diameter heptan 1 or 2-3 diameter 1 heptan or. Yes, so they are right. They are right. Good. So it means you guys are good. You guys are good. You are making my work easier today. I hope you continue with the same momentum, okay? When we get to the reactions and then the synthesis. Yes.
Yes, question 4. Question 4. I want to try.
The fourth one. Yes, go ahead.
Yes, I have 5 bromo, 2-3 dimethyl, 4 ethyl, 1 heptanol.
No.
Doc, please.
No.
Okay.
Hello?
There's
Five
nothing
bromo.
like diameter.
Hello?
5 bromo.
Yes.
Hello?
Doc, 5 bromo.
Hello?
Who is on the floor?
This
Hello?
Nina.
Yes. Yes.
Hello?
Yeah, who is saying hello? Please, the person should talk.
Hello?
Go ahead.
Wisdom.
Wisdom, go ahead.
We have 5 bromo, 2 chloro, 5 bromo, 3 chloro, 4 ether, 2 meter, heptan 1 or.
I have clap for you.
Sir, let me also. Okay. My own is 5 bromo.
No, the parent name is what?
Hepta.
Heptanol.
Yeah, heptan 1 or.
Okay. Wisdom. Wisdom, you are doing well.
I also have bromo, 3 chloro, 4 ethyl. No, sorry, 2 meter, 4 ethyl.
No.
Heptanol. No, 1 heptanol.
But why did you bring meter before ethyl? We are saying that our previous knowledge in IUPAC rules, when you have 2 organic substituents, you arrange them in alphabetical order. Ethyl starts with E, meter starts with M. So E will come before what?
Yes.
The meter.
Okay, sir.
So that is the
Okay,
name,
sir.
as you can see. That's the name, as you can see. And I'm sure, all these examples, you are writing them and the names.
Yes, sir.
As a revision material. Anyway, the lecture is being recorded, so you can always go back. Okay, somebody take the 5th one.
The lady, you take it.
The 5th one.
The fifth one. 3 heptanol.
3 heptanol.
Yes, 3 heptanol. Heptan 3 or.
Oh, yeah.
3 heptanol.
Heptan 3.
You are all correct.
Yeah.
You are all correct. Heptan 3 or 3 heptanol. You are all correct. Then the last one.
Okay. The last one.
Yes.
2,4-dimethyl hexane 1,4-diol.
Hey, relax.
Meter is there.
The biometer is only 1.
Metal is 2.
1 meter. Then
It's 2.
They are 2. It's 2. We have 2 meter.
1 is here and then 1 is here.
So please, let one person give us the name.
2,4-dimethyl hexane 1,4-diol.
Okay.
Hello?
2,4-dimethyl hexane 1,4-diol.
Hello?
Yes. Who is saying hello? Do you have a different name?
Wait on. No, it's the same thing. It's 2,4 dimethyl 1,4-diol.
1,4-diol.
It's not 1,4.
No, 2,4. 2,4.
Dimethyl.
That is 1,4
1,4.
hexadiol.
Okay,
Is it
so
hexa?
now look at the name that has been generated. 2,4-dimethyl hexane 1,4-diol or 1,4-hexane-diol.
Okay.
So you can bring the 1,4 before the hexane-diol. Okay. And then in some books too, they also write it as 2,4-dimethyl hexa. Hey. Hey. You see, online classes, people will be eating fufu and they will still be in class.
Hello, Doc.
They will
Hello,
be eating
Doc.
banku and they will still be in class.
Hello, Doc.
Yes, Joshua.
Please, with the last one.
Yes.
The hexane.
Yes.
The E is there.
Yes, it should be there. It should be there. And I'm saying that this one is correct, okay? Or in some books or in some literature, they will say 2,4-dimethyl hexa 1,4-diol. Hexa 1,4-diol. That means they will do away with the ANE. Sorry, they will do away with the NE. So it becomes hexa, HEXA 1,4-diol. That one too is accepted. Okay. Joshua, are you okay?
Okay.
All right.
Dog,
Yes.
please, me, I wrote 2,4-dimethyl 1,4-dihexanol.
No, when you say dihexanol, it means that there are 2 hexanols. And you know, hexanol itself has how many carbons? 6. So if you say dihexanol, you are referring to about 12 carbon alcohol. Do you understand? And if you add the 2,4 carbons to it, that means you are looking at what? 14 carbons. But then the alcohol there, has it gotten 14 carbons? No. 1, 2, 3, 4, 5, 6, 7, 8. That's the maximum number of carbons there. 8. So if you say dihexanol, it means that
hello?
2 hexanols. So the number of carbons even will be more than 8. Also, are you getting it?
Hello?
Yes.
Yes, sir. I was also having the same problem. So
the dye should affect the all and not the parent chain. Okay.
All right, sir.
Hello, sir.
Hello?
Yes.
If you are naming it, you can bring the 1,4 before the hexane, or?
Yes, and I'm saying that 2,4-dimethyl 1,4-hexane-diol.
Okay.
It's correct. It's the same as what it's showing. Or in some literature, instead of writing the hexane, they will say hexa. So 2,4-dimethyl hexa 1,4-diol. That is also accepted. Do you understand?
Hexa 1,4-diol.
But if you say dihexanol, that is where I was telling Owusu that if you bring the di before or in front of the parent chain, then it means it is affecting the total number of carbons, which will be more than what is in the structure.
Yeah, we said 1,4-hexane, but can it also be 1,4-hexadiol?
I've just said it already.
Okay.
Okay.
Yes.
That's my question.
Yes, France.
So you see what you are teaching. I really appreciate it from head to toe. But my question is, when do we use ISO? ISO.
Okay, Kwabna. So we are dealing with IUPAC names. Okay. In fact, when it comes to nomenclature of organic compounds, we say we have the common name, we have the semi-systematic name, and we have the systematic name. So let's say your class now, I see about 98 people here online. Now, assuming we have a number of you called by the name Kwabna, and then I called Kwabna, answer the question. I'm likely to get about 5 or 8 people who show up. What it means is that Kwabna is a common name. You understand? It cannot be used. It cannot be used exclusively to identify one person in the class. So in organic compounds, we have the common names, and the common names, depending on the geographical differences and then your country of origin, they can be used. They might be accepted. But you see, all chemists, we have a group called IUPAC, International Union of Pure Applied Chemistry. Okay, sorry. And they have come out to lay down rules that we should follow and name any organic compound, such that whatever name that is given, whichever part of the world you go, everybody will understand that name. For better way of explaining to you, maybe you are a chemist in Ghana here, and then you develop a certain drug or a certain compound. It's a new compound. Maybe because you are maybe a Ghana, or maybe because you are a Fanti, and you come from a particular locality, and per your language, you want to give a Fanti name to that compound. You want to give a Ghana name to that compound, or you want to add a Ghana language to the name of the compound because you are the first person to bring it out. And we are saying that that one is accepted, but then it's a bit localized because scientists elsewhere might not even understand your local language. So it becomes a common name. But then when we know the structure of that compound that you have developed, okay, we can follow IUPAC rules and give it systematic name, which everywhere you go, they all will appreciate and understand. So the use of the ISO, the use of the NEO, the use of the SEC, the use of the text, all these ones are semi-systematic names, which, yes, they are names that can be used, but then they are not IUPAC names. Are you getting me?
Yes, sir.
Good. So what we are supposed to concentrate and follow up is the IUPAC name, the systematic name, which is more key to us.
All right, sir.
Great.
Sir.
If you ask plenty questions, we will not go anywhere. Right? We have a lot to... Anyway, yes, any other question?
Yes, sir, please, I have a question.
Yes, go ahead, please.
Yeah. Still on the sieve structure. The sieve structure. So when you look at the other structures, there's always a trend. So for the first one, you see that we have propan, and the second one, the third one, we have heptane. Then if you look at the fourth one, we have another heptane. Now we've gotten to the sieve one, and I was expecting something like hexane 1,4-diol.
Okay, I know your challenge. So all the examples that you are giving, they were all mono alcohol compounds. There was only one OH, the functional group is only one. It is the cis one that we have two. You understand?
Yes, sir.
And that is where we are saying that when you have two of the alcohol groups, you introduce the prefix diol. If there are 3, triol. If there are 4, tetraol. So when it comes to the multiple hydroxyl groups, you more or less will write the whole corresponding alkane name before you bring the positions of the alcohol, and then if it's 2, diol. And if there are 3, so you can have something like hexane 1, 2, 4, triol. Or that's hexane 1, 2, 4. So whenever you are introducing the prefix di, tri, that one, if you go by way of writing, bringing the E, you are not wrong. And we are also saying that some books, instead of the writing hexane 1,4-diol, they can also say what? Hexa 1,4-diol. Hexa, and that one too is accepted. Or you can say 1,4-hexadiol, or 1,4-hexane diol, you are also right.
Okay.
Great. I'm happy we are done with the naming of alcohols. So now let me stop sharing this and then go back to yes, Harriet, your hand is up. Or it's an old hand.
Yes, please. It's an old hand. Sorry, say.
Sir,
Yes.
please, you said we are done with the naming of the alcohol. Does it mean that the alcohols only gets bonded to the single bonds? So
No.
we are not going to
So that's the next stage we were going, and if you take the next slide, we have sometimes an alcohol with other functional groups, like a double bond, a triple bond in there. So you can see this one. But then when you have a double bond there, still you name it as an alcohol, just that the position of the double bond is also factored in the name. So this one like this, you have what? E2-hexane 1-or. And you remember that in our alkenes too, we can have the cis and trans or the EZ system. You remember level the block 1 introduction to organic chemistry when we were looking at the geometric isomerism in alkenes. Okay, so but then in this context, I am not interested in you bringing the E or the trans. What is important is that there's a double bond there, and if you number the chain by giving the least number to the alcohol, the double bond is on the second carbon. So you start as if you are naming an alkene. So you bring the double bond position, which is 2, then it's a 6-carbon chain. So if it were to be alkene, it would be what? 2-hexane. But because it's not an alkene, but it is an alcohol, the last letter E should not come. And then you bring the position of the alcohol, then you add what? Or. So yes, the question you were asking, this is one of such examples. So in an exams, they are the ones I will be bringing more, and not the ones that I can see you are getting it easily answered.
Hello, say.
Yes.
Say, please.
Some are getting it easy, but we are not getting it easy. So please, you have to balance it.
That was just by the way.
You don't want me to score some. That's why.
I was just kidding. All right. So now enough on that. But then when I give you tutorial questions and review questions, it will expose you to some of the structures that you need to also master and then get the names right. Well, I want to finish with the alcohol, so the ethers and this. So let me just. So now let's look at the properties of what alcohol. The physical properties of alcohols. And here we are going to follow the same trend of as we saw in the hydrocarbons. We'll be looking at whether they are polar or non-polar. We'll be looking at their solubility. We'll be looking at their melting and boiling points. And then we'll be looking at their, maybe the density or something like that. So in the case of the alcohols, we say alcohols are polar compounds. Alcohols are polar compounds. Unlike the hydrocarbons, alkanes, which are non-polar. And because of that, they were insoluble in water. Water is a polar solvent, so it will dissolve polar compounds. And because the hydrocarbons were non-polar, they remain insoluble in water. But alcohol here is a polar compound. So you expect alcohols to be soluble in water. You expect alcohols to be soluble in water because of their polar nature. And I'm sure we all remember when we say a polar compound or polarization, it's just the distribution of partial charges in a molecule due to unequal sharing of electrons during covalent bonding. Okay, and so that is that. The alcohol functional group, the OH, the bond is polarized. The oxygen is partially negative, the hydrogen is partially positive. So it means that the alcohols can interact with themselves, and as well as they can also interact with water. So they are soluble in water. In terms of boiling points, they have higher boiling points than the corresponding hydrocarbons, alkanes, alkenes, alkynes. And like I said, they are more soluble in water. Now, the presence of the additional OH group in the molecule further increases solubility in water and boiling point. So here, if I give you maybe 4 compounds, one is an alkane, one is an alkene, one is an alkyne, and one is an alcohol, and I ask you which of them will have the highest boiling point, definitely it will be the alcohol. Simply because, apart from the fact that the alcohols are polar, their bond is polarized, they also engage in what we call hydrogen bonding. There is hydrogen bonding that is found in alcohols, and hydrogen bonding is the strongest of the van der Waals forces. As such, it's add up to what? The bond strength, which will require a higher energy to be able to break it. Hence, the corresponding higher boiling point in alcohols. But I'm saying that if you are also giving 2 or 3 alcohols, and then 1 or 2 of the alcohols have 2 of the OHs, then that one will have a higher boiling point than the alcohol with 1. The reason being that the more the hydroxyl group, the higher the degree of hydrogen bonding, okay, or the level of hydrogen bonding is more pronounced. And when the degree of hydrogen bonding is more pronounced, it means that will require additional energy, high temperature to be able to break it. And so there will be a corresponding increase in the boiling point of that alcohol with 2 of the OH groups or more. So the more the hydroxyl groups, the higher the boiling point of that alcohol. So if I give you, I don't know, the example that we just finished naming, where the cis one that you have 2 of the OH, it means that one will have what? The highest boiling point, because the OH is capable of what? Hydrogen bonding. So the more OH you have, the higher the degree of what? Hydrogen bonding, and as such, the corresponding high boiling or melting point. In terms of solubility, we say the alcohols are polar, so they are soluble in water. The reason why they are soluble in water is because the polar end of the alcohol, that is where the OH is, they are able to what? Associate with the water molecules through hydrogen bonding. And that's how come they dissolve in water. So if you have more of the OH, then again, the degree of association will be more pronounced, and so the water solubility of the alcohol will be more. So again, alcohols with 2 OHs will be more soluble in water than one with what? 1 OH. of comparable weight or number of carbons. Okay, because the carbon chain, which is the non-polar component, when you also increase the carbon chain, you decrease the solubility because the non-polar chain is insoluble in water. So that is that about the boiling and the solubility of alcohols. So this is just showing how alcohol form hydrogen bond with water and with itself, and that results in the high boiling point and then high solubility in water. So if I ask you, illustrate hydrogen bonding of alcohols in water, you can do something like this, and then that will be accepted. So this table is giving you a number of alcohols and then their molecular weight and then their boiling point and then their solubility. And you could see, if you compare methanol to ethane, alcohol to an alkane, you could see that their molecular weights are almost the same. But then the alcohol, the boiling point is 65, and then the alkane is what? Minus 89. Meaning ethane is a gas. Ethane is a gas. Already it exists as a gas. So very weak van der Waals forces. And so already the boiling point is negative. But then the one carbon alcohol, because of the OH and because it is involved in hydrogen bonding, look at it. The boiling point is 65. In terms of solubility, the alkanes we all know are non-polar, so you don't expect them to be soluble in water. So they are insoluble in water. But then the alcohol, because they are polar and they associate with themselves and then the water molecules, they readily dissolve in water. So the solubility is infinite, readily dissolve in water. What you can see here is that as you increase the carbon chain, you decrease the solubility of alcohols in water. The more the alkyl chain, the lower the solubility. And as you increase the number of OH groups, you increase solubility and boiling point as such. So go and study the table very well, and then you'll be fine.
Hello.
Yes.
Sir, please, can you go back to the structure you showed? Yes, please. I just want to.
This one?
No, the structure. The interaction of alcohol and water in
this
water.
One.
Yeah. Okay, absolutely. Thank you very much.
All right. Also, acidity of alcohols. Alcohols can also behave as acid. And you know, in chemistry, when you say something is an acid, that means it has the ability to what? Ionize in solution and produce H+ ions. Okay, but then when you compare the acid strength of what? Alcohols, let's say ethanol, 2-propanol, then it means that they are very weak acids. Okay, look at the pK values, 15.7, 15.9. Virtually, it means that even water is more acidic than alcohol. Is that right? Because the lower or the smaller the pKa, the stronger the acid. The higher the pKa, the weaker the acid. So alcohols are very weak acids. Okay. They are very weak acids. And then, but if you want to show or express how alcohols behave as acid, then that is it. You're able to produce the hydrozonium ion in solution. And so you can find the dissociation constant, the acid dissociation constant Ka, which will be the concentrations of the products divided by the concentration of the reactant. Okay, and then you can do that. Now, we say acidity depends primarily on the degree of stabilization and solvation of the alkoxide ion. The negatively charged oxygens of methoxide and ethoxide are about as accessible as the oxygen of hydroxide ion for solvation. These alcohols are as acidic as water, of course, weak. As the bulk of the alkyl group increases, the ability of water to solvate the alkoxide decreases, and the acidity of the alcohol decreases, and the basicity of the alkoxide ion increases. So what we are trying to say in simple is that if you have two or more alcohols and you are checking their acidity or acid strength, those with more alkyl groups, those with long chain alkanes or alkyl groups will be less acidic as compared to those with what? Short chain carbons or hydrocarbons, or those with what? Fewer carbons, which will be more acidic.
Yeah, hello. Yeah, Doc.
Yes.
Yeah, please, like as you wrote, as the bulk of the alkyl group increase that area, now, I think we use solvation when we are dealing with any other liquid apart from water. Because I know when we are dealing with liquid water, we use hydration.
No, so hydration in that context is different from, you see, here the ability of the alkoxide ion, okay, to pull water molecules to itself. That's what we mean by solvation. Is that right?
So what's the difference between the solvation and hydration? Because what I know is that hydration is when the energy generated when water interacts.
With what? Because hydration here in organic context is just addition of what? Water to anything. It's just addition of water. But what I want you to get here is simple, that if you have two alcohols, okay, and you want to assess which one will be more acidic, then we are saying that the one with what? Fewer carbons, okay, will be more acidic than the one with bulky
carbons.
Carbons, yes.
Okay, that using the ZZF rule or whatever.
The scissors rule too is another.
We have more alkyl group bonded to the it's like the tertiary alcohol being less acidic.
Yes, exactly.
Okay.
All right. Will you agree that we take some break? And then
Yes, doctor. Yes, doctor.
Let's take some break, so that those who are pounding their fufu and then doing their anwamo can go and look at it.
I'm done eating.
So it's almost 3 o'clock. Hey,
it's 2.
Oh, sorry. 3 o'clock. Almost 2 o'clock. Yes. So please, let's give ourselves some 15 minutes. I hope that's okay.
20 will be okay.
Doc.
Thank you.
Yes. Yes.
Doc. Yeah, Doc. This one there.
Doc, I beg you. The slide, those who don't have.
The slide, those who don't have.
Yes, we those who don't have.
I think 3 or 4 days ago. It's on the page, please.
So please go to your page, okay?
No, please, I've just shared it on the
We are not
biology discussion forum.
Those of you who are not on the page, there you have to private message Mercy and then others so that they add you there. Maybe they can give you, because I'll be giving a lot more materials. This course is it's a lot. So I will want you to do a lot of the work yourself. I'll be giving you a lot of materials to read. So 15 minutes.
That means exactly 2:15. We should be here.
go by that.
Hello, hello. I have been off for almost an hour now. My network. Hello. Hi,
Hello.
Jenna.
Yes.
You are on break. I've gone off for almost an hour now. My network.
Hello.
Are we set or some are still yet to? From 98 to 63. Please just inform your people to come so that we can continue with the synthesis. We are actually now about getting into the organic proper. All right. I think we can continue while the others join. Okay. So
Yes,
now
Doc.
we know alcohols, and we want to look at ways that we can prepare alcohols. This course is not only to train you for the classroom, but also to give you techniques and ways that you can make money. Okay, we know the importance of alcohol as we listed earlier on. So if you know how to prepare alcohol and you wake up one day and you are broke and you want money, you can prepare some and go and sell and get money. Okay, so I am here to also make you rich. Now, there are three methods that we want to look at. One is the hydrolysis of alkyl halides, very simple, straightforward method. Then the hydration of alkene. Now, this hydration of alkene, which is a bit, demanding, a bit detailed, we saw the same reactions in the introduction to organic chemistry. So if only you remember what we discussed then at least it's just the same thing. Then we'll look at reduction reactions, how to reduce aldehydes, reduce ketones, reduce carboxylic acids, and the esters. If you reduce an aldehyde, you get a primary alcohol. If you reduce a ketone, you get a secondary alcohol. If you reduce carboxylic acids, you get a primary alcohol. If you reduce esters, depending on the structure of the ester, you can get a mixture of primary and secondary alcohol. So we're going to take them one after the other, and then we move on. At this point, what I will want you to focus on is the chemical expressions or equations for each of the reactions. There will be the reactants, there will be the products, and there will be the reagents or the condition. You need to be very conversant with them, because in an exams, I could probably will give you the starting material and then the reagent or condition and ask you to give the products. I could as well give you the starting material, the product, and then ask you to provide the condition under which you can get the product from the reactant. So all the reactions that we're going to look at, just pay attention and be very conversant with the reactant, the condition or reagent, and the expected products. So the hydrolysis of alkyl halides, we all know alkyl halide, when a halogen replaces one of the hydrogens in an alkane, you form an alkyl halide. An example is what you see here. So a halogen bromine is bonded to an alkyl residue, and then you hydrolyze it. So the hydrolysis is just addition of water, but it can be in alkaline medium, that is a basic medium, or you can also use silver oxide. So this is the reagent, water in alkaline medium, or you can use silver oxide in what? Water. Any one of them is accepted. Now what happens is that the halogen is substituted or is replaced with what? OH. Then that forms the alcohol. Then the halogen bonds to the hydrogen in the water to form hydrogen bromide. So you know when water dissociates, it forms H plus and OH minus. So the OH minus will bond to the alkyl group and displace the bromine, and then the bromine will also be bonded to the hydrogen from the water to form the halogen acid here as a byproduct. So that is the first method of preparing alcohol.
Please, can you take it again?
Please, can you go over again?
There's nothing to go over. Everything is what is on the screen. So if you can't see well, then you need goggles. You need to go and get goggles, and then you can see, because all that I was saying is in relation to what is on the screen. If you tell me to go over again, I don't know. But then the picture here is that you need an alkyl halide. And an alkyl halide is when a halogen replaces a hydrogen in an alkane. So it could be CH3Br. It could be CH3CH2Cl. Okay. And if you know what it is, then I don't have to bother. Other than that, I will use the chem draw to draw a number of them for you. Then you add water, but then the addition of the water we are saying is in alkaline medium. So here, the reagent and then the condition that can convert an alkyl halide to an alcohol is water in H-, that's an alkaline medium. You can even write a base, or you can use silver oxide, Ag2O, in water. It also works. And I'm saying that for you to get the product right, the product of the alcohol that you are forming right, what is happening is that, you see, the water will dissociate in solution to form H+ and then OH-. Now, alkyl halides are said to be what? Very reactive, or the bond between the halogen and then the alkyl chain is polarized, because the bromine is drawing electrons, so it becomes partial negative. Then the alkyl chain becomes partial positive. So if the R is positive, then the bromine is negative, and then the water, when it dissociates, you have H+ and then OH-. Then by nucleophilic attack, the OH- will attack the positive end here, that's the R, and bond to it. So when OH is bonded to R, that's where we have this one, which is your alcohol. Then the hydrogen from the water, which is H+, will also be bonded to by the bromine minus, Br-, to also form the hydrogen bromide, which is a halogen acid. But we are saying that the main product here is the alcohol that you are forming. The hydrogen bromide is just a byproduct that is formed alongside the alcohol, which you can always purify it by removing it from the system. So that is the first method of preparing alcohol. So I don't know whether I should give a specific example. Let me see if I can.
Yes, sir.
A specific example. Just give me a minute. Please, can you see my screen?
Yes, sir.
Yes, sir.
All right. So what you find here is an alkyl halide. CH3, CH3 bonding CH3 and Cl. So apparently the chlorine is bonded to this carbon, so it's an alkyl halide. Okay, so when we perform the hydrolysis, okay, the OH from the water will replace the chlorine, and that's what you can see here. So this is an alcohol, and then the hydrogen from the water will also be attacked by the chlorine to form ACl. So when you have an alkyl halide, you could see that everything remained the same. The starting material, okay, how the structure is, everything remained the same. It's just the halogen, the chlorine, the bromine, or whatever halogen it is, that is being replaced with what? The alcohol functional group. Nothing else changes. And then you form your side or byproduct. So this is one way of preparing alcohol. So whether it is primary or secondary or tertiary alcohols, it depends on the alkyl halide, the nature. Okay. Unless I forgot, you know, alcohols are classified into primary, secondary, and tertiary. And the classification is just simple. When the hydroxyl group, the alcohol functional group, is bonded to a primary carbon, we call it a primary alcohol. When it's bonded to a secondary carbon, we call it what? A secondary carbon, a secondary alcohol. And when it's bonded to a tertiary carbon, we call it what? A tertiary what? Alcohol. So the one that we have just synthesized, this one, you could see that the OH is bonded to a secondary carbon. So it is a secondary alcohol. And if you look at the other alcohol that we named earlier on, this one is a primary alcohol. Okay, the hexane 1-ol is a primary alcohol. The 2,3-dimethyl heptane 1-ol is also what? A primary alcohol. Because the OH is bonded to a primary carbon. This one too is a primary alcohol. Then when you come to heptane 3-ol, it's a secondary alcohol because the OH is bonded to a secondary carbon. This one is a, so here, this alcohol and here is a primary, but then this one is a tertiary because the second OH here is bonded to a tertiary carbon. So for the 2,4-dimethyl hexane 1,4-diol, one of the alcohol group is a primary and the other one is a tertiary. And then if you take this one, the 2-methyl propan 2-ol, is a tertiary alcohol because the OH is bonded to what? A tertiary carbon. So again, I can ask you, I can give you a number of alcohols, their structures or their names, and then I'll ask you to classify them as what? Primary, secondary, or tertiary alcohol. So that is that. So that is the first method for preparing alcohols. Let me go back to the slide so that we look at the other methods as well. Actually, this is the mechanism, but then the mechanism is not of our interest. So the second method is the hydration of alkene. And this hydration of alkene, I said, we did consider this method when we were dealing with alkenes, the reactions of alkenes. And we said that you can react you can react alkene with water in the presence of what? An acid catalyst, and then you form an alcohol. So it just a repetition of what you learned in the introduction to organic chemistry. So this is a second method that you can use to prepare alcohol. I'm going to give you some explanation and some detailed information before we continue, but then just have a look at the illustration on your screen. Just a minute. All right, so we know alkenes are nucleophilic. They are electron rich. Water is also nucleophilic. It's also electron rich. Now, when you have two nucleophiles, there's no way they can react. They will rather repel. So the only way that you can add water to an alkene is in the presence of what? Acid. You need a catalyst. And when you use acid as a catalyst, then the alkene will react with the hydrogen to form a carbocation, an intermediate carbocation, before the water comes in to form the alcohol and you generate back your acid. You know, catalysts are not supposed to be consumed in a reaction. They only speed up the chemical reaction, but then they are generated at the end of the reaction. Now, the addition of the acid initially to the alkene follows Marconico's rule. It follows Marconico's rule. And if you remember, Marconico's rule states that when you are adding a halogen acid to an asymmetric alkene, the hydrogen from the acid should go to the carbon with more hydrogen. When you are adding a halogen acid to an asymmetric alkene, the hydrogen from the acid should go to the carbon with more hydrogen. And the rationale behind Marconico's rule is to get the most stable intermediate product, is to get the most stable carbocation intermediate, which will eventually provide or produce the most stable product, which is the alcohol. In chemistry, when you are forming a product and the product is not stable, either it will not be formed at all, or even if it will be formed, very little amount will be formed. But then again, if a product is going to be stable, that means that the intermediate product should also be stable. When the intermediate product is stable, then the product that will come out will also be stable. If the intermediate product is not stable, the final product will not be stable. So Marconico's rule, if you follow it, is just to get you the most stable product, which is Marconico's product, and which is the major product. If you do anything contrary to that, that is anti-Marconicoff, then you get what we call the anti-Marconicoff product. And anti-Marconicoff product is the least stable, or it is the one that is formed in smaller amounts because of its what? Less stability. So that is the rationale behind Marconicoff's rule. So if you take this example here, the two carbons that bear the double bond, this carbon do not have any hydrogen, but this carbon has one hydrogen. So it means that this carbon has more hydrogen than this. So the acid that is coming will come to this carbon, so that here will be CH2, CH3. And then you reduce the double bond to a single bond. Then the OH, the alcohol group, will go to the other carbon. So the two carbons bearing the double bond, one of them will pick a hydrogen, then the other one will pick the OH, as you can see here. Just that, as to where the hydrogen should go and the OH should go is what we are saying is governed by Marconicoff's rule. So if you follow Marconicoff's rule, then the hydrogen from the acid will go to the carbon with more hydrogen, and then the OH will go to the other carbon. Anything reversible is anti-Marconicoff addition, and the product will be anti-Marconicoff's product, which is always the minor product, because it's not stable, very little is formed. Now, under this hydration of alkenes, we are saying that if you form the intermediate carbocation, and that carbocation can rearrange itself to a more stable intermediate carbocation, it will do that before the water comes in for you to form your alcohol. So let's assume that you form a primary carbocation. I say more. Is it a hen or a cock or what? This is not Bronya time, or is Bronya? Bronya is getting closer. Hey. Or it's getting to Salah.
Exactly.
Anyway, all right. Okay, so that was just by the way. So if you remember, and this ones I'm making you remember, if you remember remarks, because we did look at all these things in the introduction to organic chemistry, which you have all passed, or which is a prerequisite for this course. If you have not passed that one, then you should have been doing this. But I know some few of you, I'm told, had some casualties, but we'll see to it during recits. They will pass. But what we are saying is that the intermediate that you are forming, remember the carbocation, we have stability. The methyl carbocation is the least stable, followed by the primary carbocation, then secondary. The tertiary is the most stable. So any alcohol or any product that you form from a tertiary will be formed more, will be the major product, because it's going to be a stable product. And the more stable the product is, the higher the yield. So if the product to be stable, then the intermediate carbocation should also be stable. So we are saying that maybe when you add the acid to the alkene and you form the carbocation, and let's say it is primary carbocation, that is the least stable carbocation. But if that carbocation, which is primary, can rearrange itself to a secondary, then that one will happen before the water attacks, and then you form your alcohol, so that you get the most stable product. Now that rearrangement, we did look at it, and we said the name is what? Wagner-Mewen rearrangement. That's where we talk about, if you remember, we talk about the 1,2 high shift, and then the 1,2 alkyl shift, or the 1,2 methyl shift. You either move a hydrogen from one carbon to the next, or you move a methyl group from one carbon to the next. So that is 1,2 hydra shift or 1,2 methyl shift. But let's assume that you don't want this rearrangement to take place. Whatever intermediate carbocation you get, whether it is primary, that is what you want everything to be used to form the alcohol, then you don't have to use acid as your catalyst. If you use acid, there will definitely be rearrangement taking place. So for the hydration, which will lead not into any rearrangement, we are saying that in the addition of the water, that's the hydration, you have to add the water in the presence of what? Mercuric acetate. Okay, you add the water in the presence of this catalyst, HJ into bracket OAC bracket close 2. Well, okay, that one is from acetic acid, acetate. Okay, that's how we write it. So mercuric acetate. Now, when you use this one as your catalyst, then we don't expect any rearrangement to take place. And whatever intermediate carbocation will give you a good yield, whether it is being formed from a primary carbocation or a secondary carbocation. Even though the intermediate is a less stable one, it will still give you a good yield. Now, that is what we call oxymecration, demecration. Oxymecration, demecration. So what we are saying is that first, the addition of the acid will follow McConaughey's rule. But when you follow McConaughey's rule and you get the intermediate carbocation, if there was a possibility of rearrangement, because you use the mercuric acetate, that rearrangement will not take place. And that intermediate carbocation that you have formed is what will be converted to the alcohol. And so if you don't want rearrangement to take place, then you add the water in mercuric acetate. But if you add water in an acid, HCl, or any acid, sulfuric acid, then there could be a potential rearrangement. Then the next one is called the hydroboration oxidation. It's also under hydration. Now for the hydroboration oxidation, the reaction is in two steps. First is the boration, and the second is the oxidation. So this one too, if the anti-McConaughey's product, which is always the minor product, is what you want, and you want it in good yield, then in the addition of the water, don't use acid as a catalyst, don't use mercuric acetate as a catalyst, rather use borane and THF, borane and tetrahydrofuran. And that one, when you use that catalyst, the reaction would gear towards the formation of the anti-McConaughey's product in good yield. The anti-McConaughey's product, which more or less should have been the less stable and then the least formed product, if you use the borane and the tetrahydrofuran followed by oxidation, then that one will be formed more. And that is what we call the hydroboration oxidation. So please, these two reactions, go and read more on it. I have another slide on them, which gives more information. I will share with you later. Yes, for Amma, your hand is up.
Yeah, Doc, I mean, this part, if your question
are you
Amma?
Amma and Emil is
talking. I'm using the phone. I'm using a phone.
You are using Amma's phone.
Yes, Doc.
Who is Amma to you?
She's my wife.
But the fact, I said more. I called Amma and then a deep voice response. But if you when you are joining, you could use your name. You could change the name. Eh?
Sorry, Doc. That's my wife.
Okay, anyway, the Bible says that the two shall be one, so it's understandable.
Thank you.
All right, please go ahead.
Doc, I want to find out if a question wants to come in that form, how will the question come?
If what?
If a question wants to come regarding this particular one, how would the question be framed?
Well, I think you are examination conscious. So anyway, so yes, this is how it will come. If it's a multiple choice, I will give you an alkene, okay, which when you are to add water and an acid, there is a possibility of rearrangement. And then I will ask you which of the products will be the major or the principal product. So in the multiple choice, I will intentionally bring the anti-McConaughey's product. That is, if you don't follow McConaughey's addition, that product will be there. Then I will bring the McConaughey's product. If you follow McConaughey's rule, the alcohol product that you get. Then if there's a possible rearrangement, which will give you the most stable product, that one too will be there. So when the question says that, which of the following will be the principal or the major products, then you should look at the alkene and think of whether there is a possibility of rearrangement. If it is, then you should be looking out for the one that is formed from the rearrangement as your major. Then again, if I want an answer whereby the product will be from the Markovnikov's rule, that is the Markovnikov's product, even where there's a possibility of rearrangement, it will not take place. I will change my reagent. The addition of water will be in what? Mercuric what? Acetate. Over there, if you go and choose the product from the rearrangement, you are also wrong. Because if you use mercuric acetate, it prevents any possible rearrangement. And if the anti-Markovnikov's product, which when you use an acid catalyst, we say it forms in smaller yield, is what this time around the question is saying that how do you form more of that? Then it means that I will change my reagent. I won't use water in acid. I won't use water in mercuric acetate. I will use water in what? Borane, BH3, and tetrahydrofuran, THF. That one, when you use that catalyst, it is going to give you more of the anti-Markovnikov's products, and that will be the major product. So the reaction conditions, when varied, will determine the correct answer. And that's what I'm saying, that here, at the point we are now, there are a number of reactions, there are a number of reagents, but you should try and then find a way to master them, okay, and be very conversant with them. Because this one, if you don't know, you don't know. Unless maybe you do A, B, C, D, and then you are fortunate if it's an objective test. But if you go and meet it in section B, that one you have to show reasoning. And now, in the introduction to organic chemistry, I gave you Cerelac to eat because you didn't have teeth. Now, after passing that one, you now have strong teeth. So this general organic chemistry, the assessment will be more of application. You have to think deep, okay, before, if you see the question.
We beg you. We're just managing. That dog, did we do well?
But then the theory has been published already.
Yes, we didn't do well.
Oh, is that so?
That's the DVD.
Yes, we didn't do well at all. Okay, I didn't do well.
Okay, then you let's see how it goes. But
all right,
the truth is that you survive. Okay, nobody has been killed by
just make it smile for us.
A general organic chemistry. You will survive.
Make it smile.
Inshallah.
What is important is that you will survive. Okay. All right. So the last method of preparing alcohol is the reduction of aldehydes and ketones. So if you take, there's a hand up here. Please, if there's a question asked. Yes.
Hello, Doc.
Yes, I'm
my
here.
My question is, so where do we get this material to prepare the alcohol?
Okay, so if you come for the practical, and then you enter the chemistry lab.
Okay.
All these materials are there. These reagents are there. So if you come and then maybe you have an order to give or provide alcohol to a company, when you come, I'll give you the starting material so that you can produce some 5 liters and then go and sell to maybe Casa Precon or whatever company, and you make money. All right, I will guide you. Okay.
Okay. Thank you, Doc.
Where is your center? Where's your center? Where is your center?
Sunyani Study Center.
I'm not going to
Sunyani, you will not come here. Anyway, you go to but I'm told Susek. Okay, I'm told that you are being moved from Susek to a different place anyway. Yes, but then those who will be coming to UCC, that's the UCC Center, Kaswa people, St. John's. I'll be here waiting for you for the practicals. And if you want to use some of your time to prepare alcohol, I will guide you. Okay. All right. So when we have an aldehyde, of course, this is an aldehyde functional group, C double bond OH, and then we write it CHO. Then you do catalytic reduction. So look at the reagents, hydrogen and the platinum. Then the carbon here is what is going to be reduced to a CH2OH. So you form a primary alcohol. You see, the aldehyde and then the carboxylic acid, the functional groups are always at the terminal end. So when you reduce them catalytically, you always will form a primary alcohol. But if it is a ketone, you form a secondary alcohol. Just that in reducing an aldehyde, you can use a mild reducing agent like a hydrogen and a platinum. You can use a mild reducing agent like sodium borohydride, NaBH4. But if it is a carboxylic acid, that one you need a strong reducing reagent. You need a strong reducing agent, lithium aluminum hydride in ether, followed by hydrolysis, and then you form your primary alcohol. And then also you can also reduce carbonyl compounds with Grignard reagents. That one is used to form tertiary alcohol. So if your focus is formation of a tertiary alcohol, then you need a ketone. Okay, this is a ketone, and then a Grignard reagent. So the Grignard reagent will react with the ketone and introduce the third alkyl group, and then the double bond oxygen will form the OH after hydrolysis, and then you form your tertiary alcohol. If you don't use a ketone and you use an aldehyde, you form a secondary alcohol. You form a secondary alcohol. So aldehyde are reduced to primary alcohols, ketones are reduced to what? Secondary alcohols. Then we can also reduce esters, which are acid derivatives. Now, the formation of an ester requires a carboxylic acid and then an alcohol. So when you reduce an ester, you form a mixture of alcohol. The acid tail here, okay, the acid tail here will form an alcohol, and then the alcohol tail here will form another what? Alcohol. So depending on the nature of what? The ester, you are likely to form 2 moles of a particular alcohol or a mixture of what? 2 different alcohols. In this case, you are forming a primary alcohol and another primary alcohol. Sometimes you can form a primary alcohol and then what? A secondary alcohol. And it depends on the structure of the ester. The last method for preparing alcohols is the preparation of diols. When you want to prepare a diol, that's when you want to have 2 OHs. This one too, we did look at it in your introduction to organic chemistry. You do what we call mild oxidation. Okay, so mild KMnO4 will split the double bond into a diol. Or you can also use osmium tetraoxide in peroxide, and that reagent also forms a diol. They cleave the double bond and then you form a diol. So take note of these 2 reagents that can be used to form a diol. In an exams, I can give you the alkene, give you the product, and ask you to give the reagents that can do the conversion. Or I'll give you the alkene, the reagent, osmium tetraoxide, and ask you to provide the products that will come out from this reaction. So that is that on the synthesis of alcohols. Now the last part, the reactions of alcohol. And then we are done with alcohols. Reactions of alcohols. How alcohols react. Most of them is just the reverse of the synthesis. Remember when we were forming alcohols, we did what? Hydration of alkene. We added water to an alkene and the acid. So you can also remove water from an alkene from an alcohol to form an alkene. When we were forming the primary alcohol, we said we can reduce an aldehyde to a primary alcohol. We can reduce a ketone to a secondary alcohol. We can reduce a carboxylic acid to a primary alcohol. So the same way, when you have a primary alcohol and you oxidize it, you get an aldehyde. When you have a secondary alcohol and you oxidize it, you get a ketone. So it's a reverse oxidation reduction. When you reduce an aldehyde and you are getting a primary alcohol, then when you oxidize a primary alcohol, you get an aldehyde. When you are reducing a secondary alcohol to get a ketone, when you are reducing a ketone to get a secondary alcohol, then when you oxidize a secondary alcohol, you get a ketone. Then we also have substitution of alkyl halides, then reduction to alkane, esterification, and then tosylation. So we are just going to look at them one after the other briefly, and then we move on. So this is the dehydration of alcohols catalyzed by acid. So when you have an alcohol, you can remove water and form an alkene. The typical acids that is used as a catalyst in the dehydration are sulfuric acid and phosphoric acid. But then the alcohol dehydrations are done under various conditions. Either the acid that you are using as a catalyst should be conc or dilute. Either the temperature at which you are performing the dehydration should be a low temperature or high temperature. And these particular conditions is dependent on the structure of the alcohol, the nature of the alcohol. The point is that tertiary alcohols are easily dehydrated. So within even a dilute sulfuric acid, and then at a lower temperature, you can dehydrate a tertiary alcohol to form an alkene. Primary alcohols are difficult to dehydrate to form an alkene. They are difficult to dehydrate. And for that matter, you require the concentrated acid and then a high temperature to be able to form your alkene. There's a mechanism that follows, which is here. And if you really want me to take you through, though in an exam, I will not ask you the mechanism. But what is happening is that, first of all, the alcohol that you are going to dehydrate is protonated by an acid. Then you form the protonated alcohol. Now, the protonated alcohol here is very, very unstable because the oxygen is bonded to 3 atoms and then has a plus on it. So because it's not stable, the protonated alcohol will cleave, will break away this as water. So now at the second step, there's removal of water. Now, when you break this one as water, you form a carbocation. And that step is what we call the slow step. And the slowest step is the rate determining step. The slowest step is what? The rate determining step. Now, after you form the carbocation, then the acid that initiated the reaction, that did the protonation, you need to generate it. So you go to the third step where the acid is generated, and in removing the hydrogen, its bond is broken to form a double bond to then stabilize the carbocation, and you form your alkene. This is just the detailed mechanism, which, like I said, it is just there for you to appreciate what is happening, but not to ask you to show the mechanism. So yes, another example, but I have indicated here, primary alcohols are the most difficult to dehydrate. Tertiary alcohols are the easiest. And I will want to ask if somebody has a reason why it is so. Why are the tertiary alcohols easiest to dehydrate, but the primary alcohols are difficult? Can somebody explain?
Say the question again.
There's a statement there that primary alcohols are very difficult to dehydrate, But then the tertiary alcohols are the easiest. Why? Why is that so? Or you want
So I will try. So I will try.
try.
So I
Yes.
think it's because of the position of the OH group.
What does the
OH
position
function.
got to do? What is the influence of the position?
So you were talking about the primary and the secondary.
Mm-hmm. You see, the explanation should be based on the intermediate product that you form, which I said that if the intermediate product is not stable,
I think
he said, hello, is somebody on the floor?
Sir, I
yeah, I
would
was
say
saying
that
stability.
okay. The tertiary one are
So
most
the
stable.
primary more stable.
They are most stable. That's why they are easy to do that.
Yes. So the tertiary alcohols, okay, when you move the OH, you form a tertiary carbocation, which is very, very stable. That is why it rarely will want to dehydrate, because whatever you are going to form from it is very stable. So it will prefer to be in that state. That's why it is easily dehydrated. But then the primary alcohols, when you take away the OH, when you're removing the OH, you are forming a primary carbocation. And the primary carbocations are not stable. So they wouldn't want to even get to that stage of formation of that intermediate. So before you even form them, then it means you will need a high temperature and other conditions to be able to form them. So it has to do with the stability of the intermediate carbocation, in which the primary alcohols give you primary carbocations, and then the secondary alcohol, sorry, the tertiary give you the tertiary carbocations. Now, if you look at this alcohol, it's asymmetric, okay? And if you form the primary carbocation, there's a possibility of rearrangement. And the rearrangement will lead to forming two different products, okay? The first product, which is this one, is formed from what? A primary carbocation. But when you do the 1-2 meter shift, you get a secondary, so you get a tertiary carbocation, and that is what is forming this first product. So the first product here will be the major product, and this one will be the minor product. So again, anytime you are forming a carbocation, then you should not be quick to come with your product. You should always watch out for a possibility of what rearrangement, which will lead to the most stable product before you come out with your final answer. So whatever I've explained, this is the mechanism that led to the major and then the minor product. So that's the rearrangement, conformation. And then to those of you who have forgotten, that is the stability of carbocations. The meter carbocation is the least stable, followed by the primary, followed by the secondary. The tertiary is the most stable carbocation. So whenever you are forming an alkene from a tertiary carbocation, you form more of it because then the product will be more stable. Tertiary alcohols react the fastest because they have the most stable tertiary carbocation like transition states in the second step. So I think the answer is even here. All right. So that is the order of arrangement in terms of the stabilities of carbocation. Metal is the least, followed by the secondary, tertiary, and then in that manner. So these are all giving you more examples, more illustrations. So the slide is giving you more examples over here, if you protonate the OH, and then it breaks off as water, you form a secondary carbocation. Now that secondary carbocation, if you remove one hydrogen here, you form the double bond here, and that is this product, the second one. But if you form the secondary carbocation, you can do 1-2 meter shift. One of these meter groups can be pushed here, and then when that is done, before you remove this hydrogen and form the double bond here, and that gives you this. And this product is the major product because that one is formed from what? A tertiary carbocation after the rearrangement. Formed from a tertiary carbocation. So that is the mechanism which we have already looked at. That leads to the formation of the most stable and the least stable products. Another reaction of alcohol is with the thionyl chloride. When you react alcohol with thionyl chloride, you form alkyl halide. So formation of alkyl halides from alcohol. You could as well react with what? PCl3 and PCl5. Phosphorus trichloride and then phosphorus pentachloride. You can also use them to introduce chlorine, okay, in place of the OH, and then you form your alkyl halide. Just that the use of the thionyl chloride is considered to be a neat reaction. It's considered to be a neat reaction. The reason why it's a neat reaction is that apart from the alkyl halide you are forming, the other byproducts are all gases. They are all gases. So it means the two products which are gases, you can connect a tube so that whilst they are forming, you can let them escape from the reaction vessel. So at the end of the day, by the time the reaction ends, you only will have your alkyl halide as the only product. The other products might have escaped as gases. So you get a clean product, and that's why we say it is a neat reaction. So that is that. Then another reaction of alcohol is that primary alcohols can be oxidized to aldehydes. As you can see, this is a primary alcohol. When you oxidize it, you form an aldehyde. But then the aldehydes too are also oxidizable because they have a hydrogen atom bonded to the carbonyl carbon. So because of this hydrogen, the aldehyde too can also be oxidized further to a carboxylic acid. So if I give you a primary alcohol and then I give you a strong oxidizing reagent, then don't leave your answer in an aldehyde form. Leave your answer in what? The carboxylic acid form. Because the aldehyde product will be further oxidized to the acid. If you want the aldehyde product, then make sure you don't use a strong oxidizing reagent like KMNO4, like potassium dichromate, like chromic acid. You don't use those ones, but rather you use a mild oxidizing reagent. A mild oxidizing reagent. And one of them is what you call the PCC. These ones are very strong oxidizing reagents. Sodium dichromate, sulfuric acid, chromic acid. Okay, so they will convert the primary alcohol straight to carboxylic acid. But if you want your product to be in an aldehyde form, then we are saying use a mild, a weak oxidizing reagent. And a common one is what we call the PCC. A common oxidizing reagent which is mild is what we call the PCC. The full name is pyridinium chlorochromate. Pyridinium chlorochromate, PCC. Okay, it can be used to oxidize a primary alcohol to an aldehyde. So, like as you can see down here, this is a primary alcohol. You use PCC, and then your product is in what? Aldehyde form. You also have PCB. It can also be used as well. So if you use a strong oxidizing agent, then you can only get your aldehyde when you distill it off quickly from the reaction vessel. If you don't distill the aldehyde product quickly from the reaction vessel, it stays in the reaction vessel, then the oxidizing agents, which are very strong, will convert the aldehyde to the acid product. But for the PCC, you don't need to worry yourself to distill off the aldehyde product because it's a weak oxidizing reagent. It will only convert the primary alcohol to only aldehydes, and the reaction stays as it is. So these are all examples of oxidation reactions. This is a secondary alcohol. If you oxidize a secondary alcohol, you get a ketone. If you oxidize a primary alcohol, you get an aldehyde. But then the aldehyde can also be further oxidized to an acid. If you don't want the aldehyde to be oxidized to an acid, then use PCC so that you get your aldehyde product. Or you can use the strong oxidizing reagent, but then you have to distill off your aldehyde products. This is a secondary alcohol, so when you oxidize it, you get what? A ketone. Tertiary alcohols resist oxidation. Tertiary alcohols are not oxidizable. So when you come for the practicals, we are going to use oxidation as a chemical test to distinguish between primary alcohol, secondary alcohol, and tertiary alcohol. Whilst primary and secondary alcohols are easily oxidized, the tertiary alcohols are not oxidizable. They resist oxidation. And the reason is that if you take a primary alcohol, there is an oxidizable hydrogen on the carbonyl carbon, two of them. If you take a secondary alcohol, we have an oxidizable hydrogen on the carbonyl carbon. That's the carbon that the OH is bonded to, so it is oxidizable. But if you take a tertiary alcohol, as an example is down here, the OH is bonded to a carbon without any hydrogen. All the groups on that carbon are all alkyl or aromatic groups. There's no hydrogen. And if there is no oxidizable hydrogen, then definitely it will not be oxidized. So that is the reason why tertiary alcohols resist oxidation. So these are all extra informations. And then the last bit is a chemical test. That's the Lucas test, okay? Chemical test for primary and secondary alcohols. And this one, when you come for practicals, you are supposed to do this test, okay? So the relative ease of oxidation of primary and secondary alcohols compared with the difficulty of tertiary alcohols forms the basis for a convenient chemical test. Primary and secondary alcohols are rapidly oxidized by a solution of chromic acid in aqueous sulfuric acid, and the tertiary resists oxidation. Okay, so this is a simple chemical test for primary, secondary, and tertiary alcohols. So with that, that brings us to the end of alcohols. The Lucas test is also there. The Lucas test. If you want to test for, you want to test and check the difference between primary, secondary alcohol, and tertiary alcohol, you can also use the Lucas test. In the Lucas test, you don't expect the primary alcohols to react. The secondary alcohols will react, but then it's a bit slow. It takes 5 to 10 minutes. But then the tertiary alcohols, they easily react with the Lucas reagent. Okay, within 2 minutes, you see the cloudiness of the solution. And the Lucas test is the use of zinc chloride in ACl. Okay, zinc chloride in ACl. So the zinc chloride ACl is what we call the Lucas reagent. Lucas reagent. So when you add ACl, zinc chloride to an alcohol, and if it is a primary alcohol, you will still see a clear solution. There will not be any reaction. If it is a secondary alcohol, it will react, but then it will take a longer time, 10 minutes, 15 minutes, sometimes 20 minutes. It's very slow. But if it is a tertiary alcohol, within 2 minutes, the reaction proceeds. And for you to know that the reaction is taking place, there is the appearance of what? A cloudy layer, okay, of emulsion. there's a cloudiness, and that shows that the alcohol is reacting. So the tertiary alcohol, you see the cloudiness quickly. The whole solution become cloudiness. That tells you that, oh, this is a tertiary alcohol. For the secondary alcohol, the cloudiness will happen, but then to take about 10 minutes, 20 minutes, and then the cloudiness will be a bit slow. But for primary alcohol, when you add the Lucas reagent, you for 20 minutes, 30 minutes, 50 minutes, you will not see any cloudiness because there wouldn't be any reaction taking place. So that is that for alcohols. We are done with alcohols. So do we continue with the others or we end here and continue next week?
I think we should end here and continue next week.
So that you can go and then assimilate these ones very well, right?
Yes.
Rest more.
Hello, Doc. Hello,
Yeah.
Doc.
Yes, yes.
I want to find out from you. Our practical organic chemistry, our result is not released yet. So we want to find out if there's a challenge.
Okay, there's no challenge. The challenge had been resolved, I think 2 months or so ago, 3 months ago. But then I'll follow up on it for you, okay? And then
Thank you, sir.
Make sure that, you know, I'm the chief examiner, so it's good that you are bringing this to my attention. And make sure that they publish it as early as possible before you even do this particular block's practical.
Thank you, sir.
Welcome.
Hello, Doc. Doc.
Yes.
Doc.
Yes.
Doc, we miss you. And
Hello, sir.
what I miss about it, I say we miss you a lot.
Oh, you miss me. What have you missed about me?
You say we survive. That one, you miss that one.
Oh, you survive is what makes you too. Then this time around you will not survive.
Hello, Doc.
Then this time around there will be a lot of casualties, so that you don't miss me. Somebody also said that he missed my voice.
Hello, Doc.
And that's my good friend Festus.
Hello, Doc.
Yes.
Please,
Peter,
you were talking about the things that those at the UC center that you'll be doing with them at the practical session. I don't know whether our centers to also have access to all that we were talking about.
The things to do your practicals.
Yeah, you were saying that some of them, when they come, you demonstrate for them to see how it is. So I don't know whether we do our practical session.
I'll be sharing with you that is the CHE204D, the practical component of this course. I'll be sharing the manual with you, okay? The soft copy. I'll share a manual with you. And in there, there are a number of chemical tests, okay? How to test for maybe certain functional group. How do you test for alcohol? How do you distinguish between primary, secondary, and tertiary, like what you see on the screen, the Lucas test, okay? And so I will be linking up with the practical tutors in the other centers where you'll be doing practicals. The things that they don't have, they can request, and then will supply through code, we'll supply them, and then you can go and then have a feel of it, okay? We want you to have that kind of practical experience. So we will be checking to making sure that most of the lab you do, but sometimes too, the facilities is not enough, so and you are many, so in the lab maybe at a time only one setup, and so one person will be working, and then the others will probably have to wait and then take results. Whatever the situation is, try and then make sure you always understand the principle behind all the experiments, okay?
Thank you, sir.
Yes.
The last block that we had.
Yes.
In fact, there were a lot of challenges with regards to our practicals.
What are some of them, please? Let me know.
Yes, a specific
for the chemistry, I'm coming for the chemistry practicals at all levels and at all the blocks, okay? You know, I do coordinate, even though there are other lecturers and other facilitators, I do coordinate most of the practicals and then the courses. And so if there are challenges, you can draw my attention, then we can resolve them, before the subsequent ones. So I'm listening.
Okay, so there was no specific roadmap for the practical.
The practical, okay.
Yes, so that for me going forward, let us know. I mean, if the centers can be told that I want you to conduct this practical exercise with the student 1, 2, 3, or 5 practical, which have been outlined to all the centers, so that they follow the roadmap.
Okay, so James, let me come in. The point here is that every course that you have registered has a course content, okay? And the idea is to exhaust all the content so that it qualifies you that, oh, I have done this course and I have passed, okay? The challenge here is that even if you come into the mainstream, okay, sometimes we run out of some chemicals, sometimes we run out of some reagents, and due to that, you go to the lab and some of the experiments, the technician will tell you that you cannot have it. They will rather will demonstrate it, or they will rather will explain it to you. So for that one, make sure that the practical manual I will give to you, make use of all the experiments, learn all of them, try to understand. But then, code per the calendar after we are done with the theory, okay, the 4 weeks. Then the following week is what is used for the practical. Ideally, the practical too should have been 4 weekends, so that because each practical will require about at least 3 hours, so that when you go this weekend, maybe you go and do 1 or 2 practicals, the following weekend you go and do 1 or 2. So by the time you do 4 weekends, you might have done about 8 practicals. Is that right? But we all know that the switch system we are practicing is very, very, how do you call it? Tight, in terms of the schedule. You guys don't even have a resting space. So code always give us 1 weekend for the practical, just 1 weekend. And that 1 weekend, it might even happen that it is not only chemistry practical, you might be having even physics and the other practicals. So we might not even have the whole weekend to yourself. For that reason, the manual that I'll give to you, it might be impossible to do all the experiments there. And again, I also don't want to restrict you to say that, oh, all of us, let's do experiment 1 to 3. In some other centers, they might have reagents to do experiment 5, 8, and 9. In some other centers, they might have a reagent to do 1, 2, and 3, and 4. So we are a bit flexible on that, so that whichever that your center you are able to do, you will still have a feel of it. But then you will be examining on all the experiments in there.
All right, sir. Thank you.
Yeah.
Yes.
No.
All right. Now, no more questions, because
can
if
you
not, then I'm going to continue to teach. If you don't,
No,
if
just
you don't
last
want
one.
me to end, okay, last one.
Can you
Oh, Ganas, we need the equipment.
Yes, last one, wisdom.
Yeah, it's like the stereochemistry. Then we've not registered for it as chemistry major student. Too. So I want to know whether they can bring in a program that we've not registered for us to take.
The stereochemistry that you did there, block 1.
No, there is a stereochemistry you are supposed to do in this block. That is on our timetable.
That is those who didn't do it in the block 1. Okay.
But we did it. We did.
It's electrochemistry, not stereochemistry.
Okay.
It's for the physics. It's for the physics people.
The electrochemistry.
No.
Yeah, I think it's for the physics.
Listen. The chemistry major, you did your stereochemistry in the block 1.
Yeah.
But the physics people were supposed to do it, and they didn't do it. So they can mount it this block and then do it.
No, it's not stereochemistry, it's electrochemistry.
Oh, electrochemistry is another elective. And Dr. Alberto Fori is the one to teach you.
But we have not registered for it for this semester.
It's
No
for
problem.
physics
It will be
major,
done. It will be
it's for
done.
physics people.
It will be
No.
done.
Hey, don't say it's for physics people. Electrochemistry is a chemistry major, not for all of you here. It's for the chemistry major students. Okay? Yes. It's not for all of you here. Please. The electrochemistry is an elective for the chemistry major. Those that I'm doing natural products with you, you are the ones to do electrochemistry. If you have not registered, you'll be registered.
We will be registered.
That is chemistry major students. Yes.
So that means chemistry major, they are doing their two electives this block.
Exactly. Exactly.
Okay.
That is the
But
natural product.
I don't know whether anybody has any chemistry major student have registered for that program. I don't know. But
And that's what I'm saying.
No.
Edward, and that's what I'm saying, that if you have not been able to register, maybe they've not even mounted it.
My brother,
okay?
it is there. It is on our blog. It is on our portal. It's part of our course.
You don't want me to have you.
Wait for him to
The
explain.
truth
Just
is
wait for him to
those of
explain
us
it
who are
for you.
doing, sir, those of us who are doing the chemistry major, in my case, when I registered my program, I had this general organic chemistry, practical organic chemistry, natural product, pedagogical content knowledge. These are this thing for this blog.
Do you want me to go ahead and explain?
Yes.
You want me to go ahead?
Yes.
Yes, sir.
Then allow me. If you don't want me to explain, then you call the code office and then they will give you the information.
Please, we need explanation.
Similar situation happened in the cohort 2. Those who were a year ahead of you. But we are saying that so far as it's part of the timetable this time around, you are supposed to go ahead and do your lectures, write your quizzes, write your exams. Okay? Your scores will be kept. Now, the last semester, that's the block, semester 3, block 1, they will give you an opportunity to register. Then they will enter the scores. Sometimes it's because of the total credit. They think that maybe you are doing, if you add it, it will be more than what they have captured the system. So what I'm saying is that if you are in touch with the lecturer, Dr. Alberto Fori, he will teach you like I'm teaching you the natural product, examine you, everything. And your 3rd semester block 1, you will be registered and then your results will be entered. So even if the registration doesn't go through now, it's not a problem. But then you can reach out to code. If this time around they can register you, maybe before the quizzes, they will add it as well.
Okay, sir. Thank you, sir.
All right. Bye for now.
Thanks very much.
Hey, chemistry.
Hey, Paul, hey, Paulus.
Doctor for you.
Charity. Dr. Charity, where are you?
Oh, Edward, keep quiet. Charlie, we are suffering. No.
Dr. Follow for you.
Where is Bright? Bright. Show up.